All right, good afternoon. Thank you for being here and listening to this talk. It's going to be about tasking. And tasking has been in OpenMP for quite a while, but we feel that not enough people use it. And I think that's because it's quite intimidating. It's some sort of a unconventional concept within OpenMP, but it actually is quite powerful. So the whole goal of this talk is to make you more familiar with how tasking works in OpenMP. In the old days, from an OpenMP point of view, everything had to be known. When you had a loop, everything had to be known. When you had sections, parallel sections, there was a finite number of sections that countable. So everything had to be known. And that got increasingly difficult with more dynamic algorithms. And the standard example is when you go through a linked list, you don't know when the list will end. So let me see if I can move this a little bit. Usually there was some sort of a solution, but it was ugly at best. And that's why tasking was put into OpenMP, and it was built upon an earlier tasking implementation in another compiler. So there was already some prior experience, and that came in OpenMP. And again, I'm going to try to show you how that all works. There's a big but. No formal terminology, definitions, and all of that stuff. I'm just going to explain it in normal, readable, understandable words. The lawyers have written the specifications, and I'm not going to do that. So what's a task? A task is a chunk of work, and your responsibility is you guarantee to the runtime systems that tasks can be executed simultaneously. That's pretty much the only thing you need to worry about. Okay. And this is how you do that. I'll try to show very little code actually, but sometimes I have to pragma OMP task, and whatever you put in that code block, that's going to be that independent portion of work. The rest is under control of the runtime system. Now that's a mixed blessing because sometimes you want some more control, and that's happening now. As we move into future releases of OpenMP, there's going to be more control over tasks. Okay. Right now you don't have a lot, but it's started coming. For example, when are tasks completed? So internally they're put on a queue, and that queue is being depleted as you execute the program. When do you have the guarantee that all the tasks have completed? There are implicit task scheduling points where this is guaranteed, or you can put them in yourself. Okay. Now, just for those of you who want to study things in all detail, here's the following advice. All right? Yes. And this is what it looks like. This time it stands for Recognize the Fabulous Masters. And we have this awfully good-looking guy in this shirt. You may find him or her in this booth. And they are on booth duty, and they're more than willing to help you and explain you all the ins and outs of OpenMP. Right. That's why I'm not wearing that shirt. Okay. All right. Let's get into the meat of things, the tasking concept in OpenMP. Here's the kind of the idea how you're supposed to use tasks. There's one thread that will generate the tasks. These tasks are being put onto a queue. So as they are generated, other threads that are available to execute work, they'll start depleting that queue. All right? So, and eventually when this first thread has finished, it can join the gang and start executing as well. And as I said, at some point these tasks are finished. It's well defined when that is, and there are implied points, and you can enforce task execution to be completed before your program continues. All right. So again, your responsibility is you identify the task, you use the pragma OMP task, and you put them into a parallel region, and then the runtime system, it will encounter those tasks, start executing them, and that's up to you, and then you'll wait. Okay. One of the things is there's a notion of deferred tasks. There's going to be a thing like task priorities. So There's gradually ways to control it, but by and large, this is how it all works. Okay. The important thing is there's a task synchronization point, and at that point, tasks are being executed. Okay. And again, they're implied and explicit. It's a little bit like the barrier. You know, you have implied barriers and explicit barriers. Okay. So I'm going to show you one example, and I try to find the simplest of simplest examples, because I think one of the mistakes we made when we introduced tasking, the examples were too complicated, too specific. And I found one, and you'll see me only using print statements. Right. So your task is you have to write a program that either prints a race car or a car race and maximize the parallelism in that task. All right? Well, this will be the sequential version. 3 print statements. Not necessarily the most efficient way to do that print, but okay. I got 3 chunks of work doing the print statement. And of course, what it will print is a race car, but it's not parallel. Naively, I could embed this in a parallel region. But within OpenMP, the rule is all threads execute all code in the parallel region. So I don't like asking questions to the audience, so these are all rhetorical questions. There will be some kind of question later on, but what will this print? Well, it will actually print an arbitrary combination of a race car or race car, but in a prescribed order because we're still in the parallel region. So you could have AA, race car, and all sorts of permutations of that. Although not all possible combinations, because the print statements in the parallel region will be executed sequentially. Okay, but these are possible outcomes, but it doesn't print what we got asked to deliver. All right. So, well, we could cheat and put this into a single region, and then we'll get a race car, but we'll always, of course, get a race car being printed. So that's pretty boring. And certainly no parallelism here. Well, this is where tasking comes in. What we could do, we could make printing race and printing car each a task. Now there's a funny thing here. That's one of those confusing things. Note that I still have my OMP single. Because I want one thread, and I'm going to slow down a bit here. I want one thread to generate those 2 tasks. Otherwise, I'll have, on 2 threads, I'll have 4 tasks, or 2 times the number of threads that I have. So that's not what I want. One of the conceptual issues with tasking is the task is not necessarily executed where you see it. So the tasks are generated here, but are only executed at the task synchronization point. And one of those is the barrier. Okay. So you have to think as tasks being generated and executed, and that's decoupled. That's a kind of a different way of thinking and makes tasking a little awkward, especially in the beginning. Okay. So what will this print? Well, depending on which task gets executed first, we achieved our goal. Okay. And I hope that is clear, that this is a simple way to get this done. And to preempt the question, you can do this with parallel sections as well, of course. Well, you're very good students, you did well, and quickly. So now let's add something to the sentence. I want to have the sentence end with "is fun to watch." And as I found usual when I took classes, I got a useless hint from my professor that I don't even understand what you're trying to tell me. So the useless hint here is use a print statement. Of course we have to use a print statement for that. All right. So what we do is we have our tasks, and in red is the new thing to be added to it. Now here's the challenge. This will most likely not do what you think it will do. Anybody who cares to guess why? By the way, the most active participant will get a t-shirt. So, yeah. Okay. I'll answer both.
Because the threads, the task could be after you don't secure any ordering of it.
Exactly. I think that was what you were trying to say. Yeah. Okay. You don't have that guarantee. And indeed, this is the kind of thing I ran it a couple of times, and you get fairly broken English out of your program. Because indeed, as was said, I should say that on the microphone as well, that you don't know the task typically will be executed after that print statement, because the barrier is a task synchronization point. And both the single and the parallel have an implied barrier. So the first barrier you hit is the one that is implied with the single, and that's where the task will be executed. But meanwhile, you already printed a is fun to watch. So that's why. The A was always first, because that was the sequential order. So you got it right. And that's kind of, takes a while to get used to. Right. And what we have is the task wait. The task wait is a task synchronization point, an explicit one. So what you'll do is when you put in the task wait, you enforce execution of the children tasks. And then you know when you print is fun to watch, all the tasks have been executed and we achieve our goal. So the solution is quite easy. All right. And it works as advertised. All right. The last example I want to show, that was the whole goal of this talk, is show a more real-world example. So set the stage now. And I started looking at the Quicksort algorithm. And that's what I'm now going to do. You may be familiar with it, and if so, I'm sorry for going through the whole algorithm, but it's quite commonly used. And there's a lot of sorting algorithms, but I picked the Quicksort. And it uses a divide and conquer strategy. And tasking is perfect for a certain class of algorithms. Recursive algorithms, I mentioned the linked list, and divide and conquer. There's a very natural mapping, as I hope to show, to the algorithm and the tasks. So the main steps in the algorithm, and again, I try to show as little code as possible. You choose what is called a pivot, and you split the array at the pivot point. And you're going to move the elements in such a way that all elements to the left of the pivot are smaller and to the right are larger. They're not necessarily sorted among themselves, but you know there's a dividing line between the values. And then, of course, you can repeat that for the left and right part, and you have your parallelism, okay, until you're done. So that's the high-level steps that you need to take, and this is where the parallelism comes in. Okay. So here's a very simple example, and I try to use color coding. I'm not really good at those animations, and usually animations go too quick for me to get them anyhow, so I'll do that step by step. So here's my initial, these are my initial values. The one marked green is my pivot, and one of the parameters in this algorithm is how do you choose your pivot. There have been a lot of studies on how that affects the efficiency of the algorithm. Here, for load balancing reasons, I'd like to choose the middle. Okay. Although you don't have any load balancing as you go through the data further on, but it doesn't seem like a bad choice. Okay. So I choose that pivot. I remember the index value. So I store that. And what I mark in red are the elements that are going to be interchanged. Because what I want to do, I want to move the pivot out of the way. Well, one thing is it's all in memory. You don't need any additional memory. So you swap it with the last element in the array. So 9 will go to 7 and vice versa. Okay. So that's my next step in my algorithm. And now what I'm going to do, I'm going to scan the array starting with element 0. And any element that is less than the pivot will be moved there. Okay. So with 8, nothing will happen because it's bigger than 7. 5 is less than 7, so 5 will move. So what makes the algorithm a little hard to read, there's another pointer that keeps track of places you filled. So what's going to happen next is 8 and 5. 5 will actually move and 8 will be pushed out. Okay. So that's the next step, and that's because 5 is less than 7. All right. So that's the new situation. We're done with 5 now. Okay. And we move on. As we move through the array, there's not much to be done until we hit 3. When we hit 3, we're again going to swap that with 8. All right? Okay, so that's the new situation. We have moved that pivot out of the way. As all the elements have been scanned, we restore the pivot, and now we have completed that sweep over the array, and indeed these values are less, these are higher, and we have our parallelism. All right. So we got 7, and we repeat for the left and right branch, and all you do is make these tasks. And you call yourself again. So it's a recursive algorithm, splitting things. So here's the sequential version. Always a bit tedious, awkward to read a recursive algorithm, but you go through this until you're done. You no longer have elements to sort, and that's controlled through this test. So if the lower value is less than the high value, index value, you still have work to do. So you do this partitioning. This one will return that index value, like in the middle of the array initially, and you call yourself for the left and the right branch. And this actually works. So if we want to do that with tasking, I make both branches a task. And I haven't talked about the data scoping yet. The data scoping in tasking is quite subtle, to say it politically correct. You have to really think about it. There are good defaults. The default is first private. That actually makes sense when you think about it. I'm not in favor of relying on those default data scoping rules. It's very good practice to think about it yourself. And it may be a little hard in the beginning, but it's quite rewarding. So what I usually do is myself. So in this case, we want to have all tasks to be able to access any element in that vector, because I don't know I know where they will go, but I don't want to have any restrictions. So each task can access any element in the vector, so I make it shared. I hope that is clear. These are first private, so they inherit the initial value, and that's what is being used, because I'm not going to modify them, I'm just going to read them in the next nesting level of this recursion. Okay. I need to have the driver part, and the driver, and that's why I had that lengthy introduction. Hopefully that comes as no surprise anymore, that I only have a parallel region, and I just call the quicksort, it's the first call, and I put it in a single, and because I'm a little bit paranoid, I don't want to have two barriers. The single has an implied barrier, the parallel region has a barrier I can't get rid of, so I use a no wait, because there's no reason to have an additional barrier. Admittedly, the second one is cheap to execute, but why waste the cycles? So this actually works. I mean, that's this pretty much straight from my code. But with tasking, and I didn't have time to really go into that detail, there are going to be some parameters you have to play with. For example, you don't want to generate too many tasks. Eventually you only have a few elements to sort. That's way quicker to do that sequentially. So pretty much every recursive divide and conquer algorithm with tasking has a cutoff, where you have in your code, you have a test. If there's not enough work to do, like if you only have this number of elements left, just call the sequential version. Now in OpenMP, there's a formal system. That's how people did that in the first release of tasking. Soon there was a more elegant solution called the if clause, where you have the if clause on the task, which essentially does the same. It will stop generating tasks. Okay. The mergeable will avoid, again, replicating the data environment, because each task will carry its own data environment, and with thousands of tasks, your memory consumption may get quite high. The final clause is somewhat like the if. There's a subtle difference between the two. So you have ways to control it. Unfortunately, the way it is, you'll have to experiment some with that. If you don't use these, the cases that I've seen, usually you don't get good scalability, unfortunately. Okay. So what I did, I ran this on a Spark system. That's why I work in the Spark or processor organization. Excuse me. And that's just to give you a feel for that. This is a very naive implementation of Quicksort. I mean, there's much smarter implementations out there. Given the simplicity, it's actually nice to see how well it scales. The blue, the bar chart is the runtime, elapsed time in seconds. So from 30 seconds, I get it down to about 0.7. Of course, there's a diminishing return, but I can still use 128 threads in some sort of a meaningful way. And overall, that gives me a speed up relative to the single thread performance of about 45. By the way, I also tweak those parameters to make sure that a single thread performance is pretty much the same as the sequential performance. It's another thing you want to do in OpenMP. You want to make sure that you don't lose too much because of the OpenMP infrastructure. So this is a reasonably fair speed up and not bad at all. I hope you agree. And I was reasonably pleased with it. So to summarize, we no longer need to know everything. And for certain types of algorithm, tasking is really your friend. And we start seeing more and more usage of tasking actually. As a little sidestep, yesterday in the OpenMP tutorial was mentioned, when you use accelerators, one of the beauties of OpenMP is you can combine all that stuff. So you can put your accelerator offload work in a task. And meanwhile, another task does other work. You know, very asynchronous computation. So think about it. Think about tasks in a more general way. Certainly, for certain algorithms that I mentioned, it's really a nice fit. You will have to do some additional tuning. Like I said, you have to play. These clauses have been put in for a good reason. It's not a pretty story, but it's the way it is. And remember, we do have our masters. We have one master now. So bug him with all your questions. So I'm off the hook. And I always finish with this one. That's a different talk. When people say OpenMP doesn't scale, I like to change it to say bad OpenMP doesn't scale.
Because good does.
Good does. Well, that's implied.